First of all, I want to talk about my team because I have a rather large group of people that I supervise, and all of the work that I present today would not have been possible without these people. So therefore, here on the slide, you see an overview. Actually, it was still in the early times of Corona, so the picture is a bit older by now. But you see, these are my PhD students and some of the students' helpers. And in total, my group is about a dozen PhD students and 2 postdocs at the moment. And together with this nice group of people, we've been doing all the research that I will talk about today. And as a first starting point, I want to talk about the 5 bigger topic areas we are active in. One of the biggest topics we're working on at the moment is software security, and the majority of today's talk will also be devoted to software security, specifically on automated testing of complex software systems. But in the past, we also did a lot of research on topics like control flow integrity, return-oriented programming, and other topics either on the more offensive or on the defensive side. Because for many of the topics we're working on the one hand, we take a look at how adversaries can try to compromise our systems in order to better understand how modern attacks work. And on the other hand, we also work on the defensive side to devise new techniques that help us to protect our systems. And yeah, software security is one of the main themes in my group. Then I also have a few people who work on internet measurements. So to understand on an internet scale, so basically large scale measurements, to understand, for example, how DNS security is looking like today, or how our mail infrastructure worldwide is protected. So these are then large scale measurement studies where we study the complete IPv4 or sometimes IPv6 space in order to understand certain phenomena. And these are mainly empirical studies to better understand how the attack surface looks like. Then the third focus area is privacy, with a specific focus on the GDPR, given that these are privacy regulations that are pretty prominent in Europe. And aspects like cookie banners or privacy policies are interesting for us because they have a major impact in practice. So if you're in Europe and surf to a given website, you will always see this kind of cookie banners that quite often annoy people. So we want to better understand how we can design better, let's say, cookie banners or better privacy policies, such that we do not need to ask users, but to do this, all the consent mechanisms in the background and improve privacy of internet users. Then I also have a few people working on mobile security with a specific focus on LTE and also 5G in order to understand either implementation vulnerabilities within the complex interaction between mobile devices and the infrastructure, or also flaws in the specification. And in the past, we discovered several types of vulnerabilities. For example, aspects like a missing integrity protection on layer 2 within LTE that enabled us to inject messages, and in certain configurations we were even able to eavesdrop on phone calls. And then we uncovered also some other kinds of flaws either in the specification or the implementation. And then a rather recent topic for us is the intersection of machine learning and security, because this is actually a very nice and also very emerging research area. So on the one hand, we want to analyze how machine learning algorithms can help us to improve and solve security challenges. And on the other hand, we also want to understand how robust is a given ML algorithm. So if an attacker wants to somehow interfere with the ML algorithm, what kind of robustness guarantees can we give, or what kind of attacks are possible in reality? And this is also one of the areas I'm very excited about, and therefore I first want to deep dive a bit into this intersection of machine learning and security. In the past, probably 3 years, we've worked on what we call so-called adversarial examples. You probably know them from the image domain, and we work on this area in the audio domain. And the typical use case for us is automated speech recognition. So probably many of you know, or maybe even own one of these devices. So on the slide, you see an Amazon Echo. So basically a smart speaker where you can basically speak something. Then there's an automated speech recognition that transcribes the audio into a text. And then this text is used by the device in order to understand what kind of action should be triggered. So we have a rather complex system. And for us, the challenge is to understand how robust is such an automated speech recognition system under attack. So what can an attacker do in order to somehow trick the device into doing something completely different? For this, we've also published a few websites on which we illustrate how the attacks work. So if you want to understand in more detail what we did, you can visit adversarial-attacks.net or unacceptableprivacy.github.io, where you see on the one hand some demos. So we have either audio or also video snippets in order to demonstrate how our research results look like. You find a high-level overview and then also the technical papers together with the data sets. So we've published basically from the code, research artifacts to some demo, everything on these 2 websites. And in order to understand how our attacks work, I first need to introduce how an automated speech recognition system works in practice. So the input is raw audio, so basically an audio signal. And in the first phase, we use a feature extraction. And you can, or on a high level, from a high level point of view, feature extraction works as follows. So we cut the audio signal into small snippets, typically something like 200 milliseconds. Also, there's a certain overlap between the individual snippets, and then we extract features from this small audio snippet. These features are then fed to a deep neural network. So here we use classical techniques from the machine learning area. And then the output is the specification, what the deep neural network thinks, what the audio feature represents as a text snippet, or basically just the phones, so the small parts of an actual word. And then we have a hidden Markov model that takes care of the decoding. So we have a language model that models how the different phones form individual words. And then the final result is transcription. So this raw audio signal would then be transcribed into, in this example, "Hello darkness, my old friend." So we have first the feature extraction to basically turn the audio signal into a representation that the neural network understands. The neural network performs the classification. The results are phones that are then, or that represents a distribution of what is the likely word. And then we have a hidden Markov model that performs the actual decoding to turn the phones into an actual word. So in this case here, we would have H, E, L, L, and O. So we have a transcription that the first maybe 1 second of the audio signal is then transcribed into the word hello. Then in practice, these automated speech recognition systems are, of course, way more complicated. So I do not want to dive into all these details, but here you see some numbers, and these are basically the bigger building blocks of how our attack and how automated speech recognition systems work in general. The goal from our study here was to turn one sentence that a human understands as a sentence A into something that the machine, so a smart speaker, understands as a sentence B. So we basically want to generate an audio signal that we as humans still understand as a sentence A, while the automated speech recognition system understands something completely different. And we can arbitrarily compute the sentence B such that we can basically trick the system into transcribing something completely different compared to what a human understands. So therefore, on the top left, we have the original audio as the input. And this could here be a song, Never Gonna Give You Up, or something similar. And we as humans would basically understand the lyrics of this audio signal. Then basically what's happening, first, this audio signal is turned into this feature representation that the deep neural network can process. So this is the bigger number one block. And then the output are the posteriores. So basically, it is a distribution of what the likely phones of the individual audio snippets represent. Then at the top right, we have the hidden Markov model, and the hidden Markov model is used in order to transcribe the distribution of the phones into actual words. And here, what we basically do is we have a target sentence, and the target sentence is the sentence that we want the audio system to understand. And in this case, it would be the sentence, activate remote access. So we basically have a target sentence that has nothing to do with the original audio as the input, but we want to modify the input for the system such that eventually the system understands activate remote access. So basically we want to confuse the deep neural network such that it transcribes the audio signal as something completely different. And therefore, here in the hidden Markov model, we basically have the input, the target sentence that we want to get transcribed. And this leads then to a certain posteriori distribution. And then what we can then compute is a loss function. So that's the difference between the original posteriores that we obtain when we transcribe via the deep neural network the original audio as an input, and the target posteriori distribution. So there's, in the first step, quite a big difference because the original audio and the target sentence have nothing to do with each other. So therefore, the loss function will be pretty high in the first step. Then we use backpropagation, so a classical algorithm from the ML area, where we basically feedback or where we use the output of the loss function to add or to compute some artificial noise. And this noise basically then changes the weights in the deep neural network in order to basically change slightly the transcription towards the target sentence that we want to obtain. And then we take the original audio, our computed noise, combine both, feed this again to the deep neural network. The posteriori distribution will change a bit. We again compute the loss function, so the difference between the posteriores of this modified audio together with the target sentence. And then we do the backpropagation several times. So step by step, we change the audio signal such that eventually the transcription will be activate remote access. And as an additional constraint, we also use hearing thresholds. And that's a concept you know from systems such as MP3. So MP3, as you're probably familiar with, is a mechanism to compress audio files such that we basically throw away all these audio signals that the human ear cannot understand anyways. And the basic idea is that we have a model of how the human ear processes audio signals. And then we know that certain types of information within the audio signal cannot process by our ear anyway, so we can throw them away. And so therefore we are able to compress an audio signal by removing all these signals that the human doesn't understand anyway. So that's the classical principle behind MP3. And what we use here is we use it the other way around. Because if a human cannot hear something at a specific frequency or basically or in the context of specific audio signals, then we can add some noise in specifically these areas of the audio signal. And then the human will not hear anything, but the machine will still understand that some audio information is embedded in the audio file. So therefore, the hearing threshold enables us to add noise that is unsuspectable for a human, but that the machine will still hear and somehow process. So we basically generate the audio signal such that a human cannot hear anything, but the machine is still tricked into detecting some arbitrary signal within this audio signal. And then we need to do this in a few cycles, and eventually the decoding step will lead to completely arbitrary transcription, and in this case, activate remote noise, remote access. So what we have done is basically we have the original audio signal. We have computed an artificial noise that is specifically crafted such that it tricks the automated speech recognition system into detecting something completely different. And then we obtain this adversarial audio. And if we feed this adversarial audio to the speech recognition system, then we can control what the target transcription will look like. We've published a series of papers on this theme. The first one at NDS 19 introduced the basic setup of our attack. Then we had an improved attack where we could also do this in an over-the-air setting. So we had a loudspeaker and a microphone in a room with an arbitrary room configuration. And we could actually play the adversarial audio over the air, and then the microphone would the microphone would pick it up, and this is then robust even in an over-the-air setting. And at Usenix last year, we presented a defense where the basic idea is that we made the speech recognition system more robust by modeling how a human would understand the audio signal. So the speech recognition system now uses a model of the human hearing scheme, and then we cannot prevent adversarial examples because that's a tough or maybe even impossible challenge, but we can still force the attacker in the audible range. So all attacks will now suddenly be, or we can hear and that an attack is happening. In order to illustrate how something like this works, I want to do a quick demo. So I hope you can hear this. And what I do is I first play the original audio file.
Specifically, the union said it was proposing to purchase all of the assets of United Airlines, including planes, gates, facilities, and landing rights.
So what you have heard is an audio snippet. Here you also see the transcription in the middle of the screen. And this is from a well-known data set where people read articles from the Washington Post. Then I play the noise. And here you only hear some kind of whispering or some kind of chirp, some pitches basically. But this is now specifically crafted such that we can trick the audio speech recognition system into transcribing something arbitrary. And if we now combine this original with the noise and basically just add both audio signals, then the resulting audio signal will be the following.
Specifically, the union said it was proposing to purchase all of the assets of United Airlines, including planes, gates, facilities, and landing rights.
So maybe you still heard a bit of noise because it's not really perfect. So we still need to include some of the noise here, but still you see that the target transcription is now something completely different. And we can arbitrarily change the sentence into whatever we want the speech recognition system to detect. Okay, so this was a quick deep dive into adversarial examples and the intersection of machine learning and security. And now, I want to talk about software security and what we've done there. Because what we see is an ongoing arms race in the area of attacks and defenses. For example, in Germany, we had several attacks against the German Bundestag, so against our parliament, where state-sponsored attackers were able to compromise the Bundestag and sensitive documents were exfiltrated. We've seen quite a few attacks against facilities The most famous one is still Stuxnet, but also in Germany and all across Europe, we've seen some of these attacks where, for example, in Germany, a steel mill was affected, and many other types of these kind of critical infrastructures or large-scale factories were compromised in the past years. Ransomware is still a big problem. In this example, there was an attack against Deutsche Bahn, where also many trains in Germany were affected. So a software attack actually led to a downtime of our train system. And then last year, or 2 years ago, in January, we saw a large-scale supply chain attack against SolarWinds, where hundreds of companies worldwide were affected. So what we see is that attackers seem to be able to compromise complex systems, and the root cause are always software vulnerabilities. For example, in Deutsche Bundestag, the entry point was likely a software vulnerability that was then used in order to obtain access to a machine, and from there, privileges were escalated. Ransomware, the typical first step is that also a software vulnerability is used in order to compromise one of the machines, and eventually the attackers want to control, let's say, the domain controller and then start to encrypt files. Or with SolarWinds, they were able to compromise the build server and then inject a backdoor into the system that was then distributed to companies. So it seems like we can, in principle, build software systems, but once they reach a certain complexity, we somehow fail to build them in a robust and sustainable way, because attackers seem to be able to find vulnerabilities in a more or less easy way, and then they can use these software faults in order to compromise systems and then steal sensitive information, or somehow break confidentiality or the integrity of data. In order to understand what we can do against this, we first need to take a look at how these attacks typically work. And one of the main techniques are so-called code injection attacks, and they work as follows. On the left-hand side, you see a so-called control flow graph for a program, because you can represent each program, so each binary executable, as a graph. So you have an entry point, that's basically the first instruction that is to be executed. Then you have a sequence of instructions that are executed one after each other. For example, a few assembler instructions that are executed. And then eventually you will also have the possibility to jump to another position. So basically we have nodes, and the nodes are then the small building blocks, and we call them basic blocks because they have a single entry and a single exit, and in between there's an arbitrary number of assembler instructions. And the basic blocks represent something like the atomic units of a program. Two basic blocks are connected to each other via an edge if we can jump from one basic block to the other. And because we have this single entry, single exit policy, this means that the basic blocks need to be executed one after each other. So each assembler instruction needs to be executed, and we can only leave a basic block at the end. So therefore, this control flow graph nicely represents what kind of control flow decisions the program can actually do in practice. Now we have an attacker, and the attacker knows about a specific vulnerability. Let's say he knows there's a buffer overflow or a use after free or some other kind of vulnerability in basic block A. And what the attacker then does with a code injection attack is he basically sends data to the vulnerable part of the program. He triggers the buffer overflow. And what he also does is he injects his own code. So typically that's so-called shell code, so code that the attacker wants to execute. And then by taking advantage of this software vulnerability, he can then lead to a control flow deviation. So the program, once it has stopped to process basic block A, does not jump to basic block B in order to continue the normal execution, but the attacker forces the program to jump to this block D, where code that was injected by the attacker is located, and then the attacker can perform arbitrary computations. For example, spawn a shell or do other kinds of malicious kinds of computations. So code injection attacks, the attacker injects his own code into the address space of the vulnerable program and then forces the program to jump to this injected code by taking advantage of a software vulnerability. The modern variant of this kind of attack is so-called code reuse attacks, and they work in a very similar way. So again, we have the attacker knows about a vulnerability here in basic block A, but because many defenses were proposed and then also implemented in practice, just injecting code into the address space of a program is not that easily possible anymore these days. So therefore, attackers resort to so-called code reuse attacks, where they take advantage of the fact that the vulnerability is still there, because fixing all vulnerabilities is very challenging in practice. And what the attacker is now doing, he does not inject his own code, but he reuses existing code that is available in the address space, that is maybe even checked. So maybe a signature was checked. This code is executable, so the memory pages are marked as executable. And so what he does, he forces the program then to jump from A to C and not to B. And this means that he can still perform malicious computations. Of course, the attacker is way more restricted, but in practice, this is still enough in order to be able to perform meaningful malicious computations. And so what we've done in the past years is we worked quite a bit on this whole theme of how we can prevent code injection or code reuse attacks. And the main advantage here with the code reuse attack is that there's no new node in the control flow graph, but only a new edge. And this is more stealthy from an attacker's perspective, but still there are ways how to prevent this kind of attacks. And what we've been doing is we worked a lot on this kind of topics, for example, on so-called data execution prevention, so where we make sure that only code or only data is executable. For example, for microcontrollers and other smaller embedded systems, we devise techniques how to build data execution prevention in an efficient way in order to also protect microcontrollers and other parts of a machine or some more complex industrial system against attacks. Address space layout randomization, where we randomize the address space, is another popular method in order to prevent this kind of attacks. And there we've proposed some schemes also how to do this in an efficient way for embedded systems to protect them against this kind of attacks. Stack canaries, there the idea is that we have certain areas in the address space where we can detect if they were overwritten. And this is then a strong signal that indicates that an attacker was able to override memory. And therefore, what we do is we use this as some kind of easy way to detect that the memory was somehow corrupted. Another promising area is so-called shadow stacks, where the idea is that we have a copy of the stack, so basically a copy of all the meta information about the control flow, and then we can also detect whether something was overwritten or not. And I think shadow stacks, given that they are now also used by Intel as part of the processors, they are probably one of the most promising ways how to defend several different classes of software-based attacks. And then there were a few PhD theses actually about this topic, control flow integrity, where the idea is that we enforce the integrity of the control flow. So we make sure that only legitimate control flow decisions are taken. So we basically enforce that the control flow graph from the previous slide is followed, so that only we can jump from one node to the other if there's an edge between both nodes. And we implemented this for different types of systems and made sure that this is performant. And this is actually a very promising technique these days, because also Visual Studio, GCC, LLVM, and other compilers support this. So if you compile a program with a modern compiler, you will have CFI as a compile time option. Systems like Android or now also Windows use CFI in different configurations. So this is a technique that is being rolled out by now, and this will also make software-based attacks more challenging in the future. Execute-only memory is a technique we worked on, and I have a few slides related to this next. And then there are many other techniques that were proposed, like write integrity protection. And yeah, the main question that I and my group are working on, and many other groups in the world too, is which of these pieces are actually needed? How do we combine them efficiently to make sure that software-based attacks are more challenging? And how can we implement them efficiently, either on the software or on the hardware level? And the goal is to basically come up with a solution that makes attacks way more challenging, that we can stop several different classes of attacks from the root cause, such that they help us not as only a band-aid solution, but rather to prevent certain types of vulnerabilities at the core, and then how we can implement them efficiently, such that we can also deploy them in practice. And here I want to dive a bit deeper into one of the papers we published at CCS 2014, and I still like the paper, although it's a bit older, because it's a very simple idea that is actually, I still like it very much. There are also now hardware-based implementations of this idea, and what we enforce is a very simple primitive or an invariant that should actually hold. And as the name suggests, execute-only memory means that code, or maybe explain it different, one of the strength of our current computing infrastructure is that we have a rather simple way how to build memory. Because in memory, we can store code and data, but we do not have any kind of indication where code or data is located. So at arbitrary locations in the memory, we can store code and data, and at runtime, we decide if this piece of memory should be interpreted as code or should be interpreted as data. So classical von Neumann principle, we can store arbitrary information in memory, and this can be either code or data, but we do not really differentiate. So we do not have something like only a code memory and only a data memory, but one large address space in which we can store both. But what we want to enforce is that code, because code are the instructions that we want to execute, and we only need to execute them. So we do not need to write them, we do not need to modify them, and we do not even need to read them, but we only need to execute them. And this is classical access protection, where we have our classical access control method of we differentiate read, write, or execute. So the classical 3 bits that you also know from file systems and in many other contexts. And what we enforce is that these 3 bits are actually represented individually. Because it turns out that in practice, typically when you can execute something, you are also allowed to read it. But actually, we do not need to read memory if we just want to execute it. So what we basically enforce is that whenever we execute code, we are able to do this, but we are not able to read or write code in memory. And this is basically what the CPU is doing anyways. So first, the CPU fetches the next instruction to be executed. So the instruction fetch reaches out to memory, to a code location, reads the instruction, then this instruction is executed. And then we can also load or store. For example, we can load parameters or store the result. But this load and store instruction should only interfere with the data area, but not with the code area. And so this is the classical von Neumann cycle that you see on the left. We fetch something, execute it, and then store the result. And what we then also do, we enforce this execute only property at the CPU level. And to do this, we also had to modify the kernel a bit to make sure that the page fault handler actually differentiates whether we have an execute access or a read access, because the classical page fault handler just assumes that whenever we want to execute something, we also are able to read this location. So therefore, we had to add a new type of access control here, such that when the access type is read, then we also make sure that we differentiate whether the area is code or data. And when it's a code area, we basically kill the process, because the process wants to read its own memory, and this is something we do not allow. But if only we read data from memory, then this should be allowed. And then what we did is we basically modified the page fault handler to make sure that this invariant is implemented. And this was a bit complicated, because we also had to make sure that if the access type is execute, that we make sure that we maintain, in this case, a sliding window of pages that are allowed to be executed. And it turns out that in practice, this introduces a bit of overhead, but also not too much of overhead. Because if we take a look at some classical CPU benchmarks, we see that the overhead is for some programs, for example, Xalan, it's a bit higher, around 8 to 15%. But for many of the programs, it's less than 2% of overhead. And the mean overhead across all is roughly 2%. So enforcing that code can only be executed but cannot be read introduces a bit of overhead. But what the nice property here is that the attacker can then not read code. He cannot really modify the code that is available. So we certainly limit what an attacker can do. And by now, ARM processors actually also implement this property in practice. So execute only memory is something that can now also be used in production. We also measured the distribution of page faults, and then we saw that for some programs, the page fault duration was a bit longer. So you see a longer tail, because sometimes it takes longer to process this, because we had to implement this sliding window. But for many page faults, it's roughly only 10 milliseconds. So this is tolerable. This is actually feasible in practice. Okay, and then, in the last minutes, I want to talk about software testing, because that's an area we are working on a lot recently. And here we have a system that we want to test. This can be a software system. This can be a microcontroller that's used as part of a more complex, let's say, factory or something like this. And then we have an input that we can send to the system that we want to test. And if we send this input to the system that we want to test, typically there's not too much interesting things that happen. But what we do is we perform some kind of mutations. For example, we flip a 0, or we append random inputs in the middle, and then we send this mutated input to the system. And then we hope that something interesting will happen. Of course, if we do only a few mutations, then not too much interesting things will happen. But you can think of this as this horde of monkeys that have typewriters. And if they just randomly type on the typewriter, eventually they will also write a poem of Shakespeare. And we use the same principle now for efficient testing. So we send a massive amount of random inputs to the program. Of course, not monkey style that we just do random mutations, but a more crafted kind of technique. And then we hope that we find interesting crashes. The underlying technique was devised in 1988, so print is still quite old, but these days is one of the most active research areas in academia and also in practice, where companies like Facebook or Google invest millions into fuzzing. So The modern way to do this is so-called coverage-guided fuzzing. Again, we have the system that we want to test, and we have a software representation of the system. So these are basically the control flow edges, or here you see control flow representation of the program. We have an input that we send to the system and a mechanism to observe what the system is doing. Then we do our mutation, send this mutated input to the system, and then we can observe that all the areas in green are executed. So this input is then interesting for us because it tells us how to reach all the areas in orange that are now highlighted on the slide. We do the same thing again. We take the input, mutate it, send it to the system, and again, this green area is executed. So therefore, this second mutated input is not interesting for us because it doesn't provide us any new type of information, because the first mutated input already tells us how this green area can be reached. But what we can do, again, mutate this one input, send it to the program, and then another area of the program is executed. So here we then have new input. This is then interesting for us. And then the combination of this first and second mutated input already enables us to cover quite a bit of the control flow graph of the program that we want to test. Internally, the fuzzers store this information about what kind of area was covered via a bitmap. So that's a lossy representation that I want to come back to later on. And then what we've been doing is we did a lot of work on working on the challenging cases. So basically how to cover parts of the program that are not easy to cover. And then in the past, we found hundreds of software vulnerabilities via our techniques. Unfortunately, visualizing this kind of software testing is hard in practice. And therefore, what we did is we built a demo in order to show how this works. And here you see this Super Mario game that probably many of you are familiar with. Probably you played this 20 years ago. And what we did is we used our fuzzer, connected it to Super Mario, but we didn't implement any kind of game logic. We only basically told the fuzzer to maximize the X value, because the task here is that Mario generates a sequence of inputs such that Mario reaches the end of the level. That's at the far right in this case. And then we only encoded information such as if the character dies, then we need to start from the beginning. And if the character doesn't move on, we also kill it after a few milliseconds, such that the fuzzer also generates key presses. And then if we then do this automated fuzzing, so basically maximizing the code coverage, then we see the following result after a few thousand iterations. And as I said earlier, we didn't encode any kind of game logic. So we didn't teach the program what the program needs to do, just that it should maximize the X value. And then you see actually not bad how the computer learned how to play this, especially here at the end. And then, yeah, after probably 30 seconds or so, the Mario was at the end of the level. In order, basically, as I said, a visualization. Oh, sorry, this was the wrong direction. And here you see a representation of how this evolved over time. So you see over time, Mario learns how to basically jump over specific enemies, or how to also avoid falling here into a trap. So the fuzzer seems to figure out over time what the right sequence of character presses should be in order to reach the end of the level. And then we also implemented quite a few fuzzing tools. All of these tools are available on GitHub. So if you want to learn more about what we've done, go to github.com/rob-sysec, where you find implementations of our tools. And the basic idea is that we build a custom hypervisor called KFL. And within this hypervisor, we encode all the fuzzing logic. And the hypervisor also enables us to boot virtual machines. And in the virtual machine, we can then either have kernel or userland applications that we can then efficiently test. And the nice feature here is because we have our own hypervisor and we can run everything in a virtual machine, we can also do snapshots of the full system. So we can bring the system that we want to test into a specific configuration, do a snapshot of the full system, then iteratively explore the system that we want to test. And then once we see that we do not have any kind of meaningful progress, we basically reset the snapshot, restart from the beginning, and then we can do this very efficiently. This is then a bit complicated, so I don't want to dive deeper into this, also due to the time. But the efficiency here is that we can do the snapshot setup in a short amount of time. And then we can even use something complex such as a browser. So we can basically start something like Firefox, let Firefox initialize all these hundreds of megabytes of code, all the interfaces that are needed to run the browser, then do a snapshot, and then only start to explore specific interfaces. And this is very efficient, and Mozilla is looking at using our tools. So they are integrating our so-called Nux-Fuzzer into their production testing, for example, to test the IPC interface, because the appealing property here is that via the snapshot of complex full systems, we can actually do the testing very efficiently. Because resetting a full virtual machine is actually rather cheap in practice. So here you see how efficient this is. We can do a few hundred, maybe even more than 1,000 snapshot restores per second, if only a few pages are dirtied. And this means that we can actually take a full system snapshot and reset it, as I said, a few hundred times per second. So fuzzing is then orders of magnitude more efficient. And then as a last slide, the outlook, I think what we want to do in the future, or where interesting research problems are still open, is a better understanding of from the software we attack vulnerabilities at the hardware layer. So Meltdown, Spectre, and Co. and all these vulnerabilities have shown that from the software side, we can also trigger hardware vulnerabilities. And there we need to better understand the attacks and also device defenses. The efficient co-design of hardware and software for memory safety. So what kind of defense techniques should be implemented on the software level? What defenses should be implemented on the hardware level? How we can connect them better is an interesting challenge. And for software testing, especially for stateful systems, such as cryptographic libraries or a TPM or other, let's say an LTE stack, there we need better ways how to model and how to test them. How can we synthesize inputs more efficiently, such that we can cover the whole input space efficiently? And then towards automated exploit and patch generation. So can we automatically find the root cause of a vulnerability, devise a way and open challenges in the software area. And with this, I would like to conclude, and I'm happy to take questions. Thanks a lot.
Thank you, Thorsten. The presentation was very large in terms of topics. So I think you've been going through a very wide range of basically possibilities on where we can apply software security and the challenges. So I'll start basically with the people who are online and ask them if they have questions. So there is one question from Vikas Sharma already. And the question is, some programs may have functions like virtual alloc and virtual protect. Will they be identified as malicious? If not, then how will we protect such programs from attackers, as these are imports in import table or dynamically loaded via load functions? I don't know if the question is clear.
Dr. Madhuvan, this was from me. I was using this link which Vikas gave me. Somehow I'm visible as Vikas.
Sorry.
And now I'm visible as you. So I'm not sure what I have to do to be visible as Yogesh. I don't know.
Okay, then you just can ask your question then orally. If it was yours, it's even better. Hello,
So
Yogesh?
yeah, that's the question, sir. Yeah, if they can answer, it's good.
So
That's the question, sir. Yeah, if they can answer, it's good.
Okay.
okay, so yeah, functions like, let's say, virtual alloc or something like this, they are not malicious per se, because in many legitimate programs, of course, you also need to allocate memory, and so that's a normal function that is used. So, but for our testing, this is actually no problem, because what we still see, or what we see, is that the program just allocates memory, maybe writes something in this memory space, and then we, yeah, basically, actually,
So in the process, if some, sorry. So in the process, the pages are being changed. The access for the pages are changed dynamically. So when it comes to your slide, when you were talking about making the pages like only write only or only execute only memory, then
execute only, okay, of course. Yeah, so execute only memory doesn't work for things like JIT engines or something like this, where you also generate code during runtime. So JIT engines, or let's say even in the kernel, if you have eBPF functions that also dynamically generate code, then this doesn't work. So for these cases where you need to at runtime generate code, then these pages cannot be protected via execute only memory, but this can only be applied to code that is known at start time. So when you load the code, then you can mark these pages as being execute only, and then they cannot be abused anymore. So this defense specifically prevents everything that is just in time code reuse. So basically where the attacker during runtime starts to build a rob chain or something, then we prevent that the attacker reads memory and then basically builds a rob chain. So we prevent the attacker from disclosing the memory space during runtime.
all right.
This answers the question.
Yeah. Got it.
Okay.
What do you propose in these situations? Like we alternate methods for because a lot of code that has been written is using, most of the malicious codes are being using these kind of functions, and like if any genuine program also has these kind of functions, then the attacker may use already, because he doesn't have to write the code into the memory. He can just use the same functions which are imported for doing the job that it can do for his own benefit. So in that scenarios, I maybe out of the scope of the presentation, but something which we can talk about.
Yeah, so for JIT engines are very hard to protect in practice, given that they have very high performance requirements, because they are designed to execute code as fast as possible. So therefore, securities, they're always a trade-off. There were some proposals to use control flow integrity, such that basically when you generate code, you also generate a CFI policy that can be enforced when the code is executed. But then this again introduces some kind of overhead. I think from top of my head is, I think, about 8 to 9% performance overhead for this on-demand CFI. So that's challenging. There were proposals to separate code generation and then code execution. That works to a certain extent. And then also in practice, V8 or other JIT engines from, let's say, Chrome or from Firefox, they also implement several techniques in order to protect JIT engines against potential attacks. But then if you take a look at the CVE entries, you see that attackers are able to find lots of vulnerabilities in JIT engines. And in practice, this is also one of the main attack vectors. But the Chrome team, so V8, they're also looking into developing new defenses. And I think over time we'll see, or we'll also see also deployed in practice more defenses. So if you compare JIT engine protection 5 years ago from what we do today, I think we've seen huge steps in how this can be made better. And eventually we will get there, I think.
Thanks, Professor. Thanks for answering.
So are there other questions? I'm seeing Sanjay. Sanjay is asking a question.
Yeah, thank you, Thorsten, for the nice presentation. So I have question rather, I mean, it's not the question as per on the presentation itself, but on a larger thing, especially because you were just talking about security and performance, and definitely people try to, you know, not balance, even just want to, you know, compromise one over the other. And especially it's very true for mitigation part. And so for example, you were also mentioning about control flow integrity, and then we also have data flow integrity, and we can definitely go much fine grained, but normally we can't do it because it says, well, you have a lot of performance overhead, so you can't do it. And I just feel that, okay, now I think, don't you think that it's like we have to now really think about like optimizing things for the security rather than performance all the time, because performance is anyway, I feel super nice nowadays. And if we have fine grained control flow integrity, for example, or maybe control data flow integrity, things should be good. But we still, I mean, I see very nice proposals, but sometimes they are just rejected because, oh, it's high performance overhead. So what are your, I mean, thought on this? I mean, why we are really rejecting that? Okay, no, it cannot be more than 5%. I will not take it.
Yeah, this magical 5% is actually something I also worry a bit about, because in practice, given that we have so high performance CPUs these days, and many users will probably not even notice a 10% or 20% cut in the performance, but still the software companies are a bit reluctant to deploy something like this in practice. So what I think will help is, on the one hand, where Intel and other CPU vendors are adding defenses right in the processor. So for example, with Intel CET, we will see a shadow stack, and also, okay, it's a coarse grained CFI, but still it's the first step towards a better CFI solution directly embedded in the CPU. So therefore, it's rather transparent, and we do not see any or not much performance overhead. And then on the software level, I think if we can convince, or if we build some of the defenses into our compilers, then the users or the vendors can decide whether they want to enable or disable it. And with Android, we now see that even CFI with a more fine-grained policy is deployed in practice, because also on these mobile devices, the CPUs are fast enough such that you do not probably notice a certain delay. And I think because CPUs are getting so much faster, we will see more and more of these defenses being deployed in practice, and via the compiler and also CPU support, we also make it easier for developers to actually use this in practice.
Yeah, I mean, definitely this is because we saw, like, I mean, I remember, like, even for the examples of the CFI, like for example, tough call. We know that we were doing something, and we were cautious, like we could have done more, for example, function signatures, but it was just like argument and return, but we could have gone more, and we could have done more and nicely, but performance was the bottleneck. No, we can't do it because people will not accept it at all.
Yeah.
And then I feel like, yeah, well, what to do about it then?
Yeah, that's good question. So actually so in the academic papers, we typically have this 5%. We try to, because some of this also maybe also a myth in the whole area, because finding this origins is pretty tough. There were some papers from Microsoft who claimed that this is something what Microsoft is tolerating. But then if you talk to teams at Microsoft or at other software companies, it really depends on the application domain and what kind of security properties help. So I think performance is, of course, it's challenging. And I think in many application domains, it's now changing. For example, if we talk to companies in the embedded space, they can tolerate this because typically the microcontrollers are fast enough that even something like 20–30% slowdown is acceptable because the machine can still perform all the computations that are needed. But if we can then protect against software attacks, then the manufacturers of the machines are happy because they don't need to worry about this in the future.